Today we're gonna talk about how airplanes generate lift. A really famous scientist by the name of Daniel Bernoulli made groundbreaking discoveries in the field of fluid mechanics in the year 1738. In his book, Hydrodynamica, Bernoulli explains the behavior of fluids in motion and explains the basics for Bernoulli's principle, which relates pressure and velocity when a fluid is flowing. Bernoulli discovered what is known as continuity, which in simple terms means that the rate at which fluid mass flows through a pipe must remain the same, or in other words, constant. Mathematically, the concept of continuity is explained by the equation area 1 times velocity 1 equals area 2 times velocity 2. The continuity equation demonstrates that if we have a decrease in the cross-sectional area of a pipe, the velocity will drastically increase due to the fact that mass must be conserved.
Continuity is just a derivation of the Bernoulli principle, which explains how an increase in the speed of a fluid results in decrease in its pressure.
Mathematically, the Bernoulli equation is expressed as pressure 1 plus a half times density times velocity 1 squared plus density times gravity times height equals constant, or in other words, the sum of the static pressure, dynamic pressure, and gauge pressure must remain the same throughout the pipe.
The continuity of Bernoulli principle demonstrates that as the cross-sectional area of a pipe decreases, the velocity of the fluid will increase, and consequently there will be drastic decrease of pressure.
Bernoulli's principle is clearly seen in venturimeter-type systems, which look something like this. The fluid will enter a venturimeter's area at a certain velocity. Subsequently, the area will converge at the throat, which will result in an increase of the velocity of the fluid and a drastic decrease of pressure in that area.
The area will then diverge once again, and the pressure will increase and the velocity will decrease to its original value. Now, if we take a look at an aerofoil, which is the structure of a wing in 2 dimensions, we can finally explain how the airplanes generate lift. Then, the principle of this is exactly the same as what we can see in the venturimeter.
The air particles move towards the wing, and when contact is made, air is split between the upper and bottom surfaces. As you can see, the top surface of the wing has a smaller area to pass through. Therefore, we will have an increase in the velocity of the fluid and a decrease in pressure. The opposite will happen in the lower surface. We will have an increase in pressure and decrease in velocity. This difference in pressure will push the wing up and will result in a pressure distribution throughout the wing, and a point called the center of pressure will be created, which is where the resultant aerodynamic force is present, with lift as the force in y and drag as the force in x. Let's imagine an aircraft on the ground wanting to generate lift and take off. As the aircraft starts moving and the fluid starts making contact with the wing, as explained before, a pressure difference will show in the aerofoil or wing. As the aircraft starts gaining speed, due to Bernoulli's principles, the pressure difference will start to gradually grow and get bigger. As this difference in pressure grows, the magnitude of the lift and of the resultant aerodynamic force will simultaneously grow with it. The pilot will continue to increase the velocity of the aircraft in the ground, and therefore increase the difference in pressure on the wing as well. Once the difference in pressure between the upper and lower surfaces of the wing is large enough for the lift to overcome the weight of the airplane, it will finally leave the ground and fly.
In the year 1883, another scientist called Osborne Reynolds discovered that the fluids can flow in a laminar or turbulent way. He found a non-dimensional number that determines whether the flow is turbulent or laminar. The equation for this number is density times velocity times diameter, all divided by viscosity. There are different types of airfoils, each with different curvatures.